So this talk is about, as the title says, a fast REST JSON tokenization microservice. So there's a few keywords in there. REST, JSON, obviously. Tokenization is basically turning sensitive credit card numbers into harmless tokens and vice versa. A microservice, well, we're gonna look at that. What is a microservice, right? Okay, it's a small thing focused on doing one thing well, as small as can be. And yes, in another talk, somebody said, right, big chicken, which is the big app versus little tiny Mac nuggets, right, which are the microservices. So it is autonomous, so many microservices can communicate via web, via HTTP, and they can run on their own servers, or maybe a few of them, you want to load them for efficiency on one virtual machine. And in this context, as I already explained, it's an NGINX plugin that tokenizes credit card numbers and back. So what's the motivation for this project, right? So essentially, it was a failed project which I rescued, right? It was initially coded in Python. Any laughs here? No. Under Django. And why was this done? For ease of for a quick time to market, essentially, right? And then we had abysmal performance, right? And then I volunteered to rescue this and do it the right way as a microservice under NGINX, NGINX being awesome. So yes, you can obviously rescue other implementations, right? You could have another slow server like JBoss, which handles up to 20,000 requests per second, according to this web link here. Or Tomcat, which handles 3,200 requests per second, according to this other web link here. And well, what I wanted to do is 1,000,000 requests per second, right? Okay. Have we achieved this? Let's see. So again, let's bash Python a little bit. It's the afternoon. I want to kind of engage the audience here a little bit, right? The first rule of Python is you don't talk about the global interpreter log. The second rule of Python is you don't talk about the global interpreter log. And there's a guy named David Beasley who benchmarked actually a CPU-bound code on a Mac Pro, and a CPU-bound code could be, encryption, for instance, right? It's one of the classic examples of being CPU-bound. So a sequential operation took 7.8 seconds, and then he cut the workload in half, right? And gave it to 2 threads, so only half the workload to 2 threads, and they took then 15.4 seconds to finish. So, so basically, he didn't solve the problem, he made it worse, right? And 4 threads took 15.7 seconds, right? Right. Well, let's talk about the motivation. What if you are a hardware company in 1996 or something, and you don't selling your high-end servers, right? Well, you create an interpreted language. Welcome to Java, right? So now you're selling your high-end servers, right? Okay. But at least it multithreads well, or does it, right? Because the classical Java model is the synchronous multithreading model. So I've seen Tomcat with 2,000 threads, and it doesn't really work very well. Dispatching becomes a problem, right? Which thread is really ready? Which thread is the next one which should actually run, right? Just as a recap here, NGINX offers processes and threads. So what are the advantages now when you code this in C, which is an awesome language, under NGINX, which is an awesome web server? What you can either choose multiple processes or you can choose multiple threads, right? So there are pros and cons, different different ways of doing things. So in processes, you have to implement shared memory by means of memory map files, right? And I was just in another talk, and the guy did it that way, right? NGINX, okay, was the talk. And then you have to implement caches either separately per process, which the guy did, it's exactly what he did, or inside a memory map file. You can do that, and then obviously you have a global cache and you lock it properly. Or you can choose a threading model, and we didn't get this to work for some reason. We had limited time, so we actually chose multiple processes. But conceivably, NGINX supports multiple threads also. And then obviously, very obviously, right, each and every static and global variable is shared, and you have to lock the access. And automatic variables and heap memory are per thread. So now let's focus a little bit on synchronous versus asynchronous multithreading real quick. As we all know, NGINX is asynchronous, right? So it's, which is the way it should be, but let's, just for the sake of argument, let's talk about synchronous multithreading a little bit. Each and every thread can basically block on I/O being, file I/O, network I/O, database. And thus we need lots and lots of threads because, right, some of them could be blocked, or many of them could be blocked. And so on one of my former employers' Blue Coat systems, they wrote an OS from scratch to support tens of thousands of threads. I'm not making this up, right? So it's basically, it's called SGOS, and it supports whatever, 40,000 threads, right? Because Linux doesn't, right? Okay. Linux does it theoretically, but it doesn't really dispatch them well, and then it consumes too much CPU cycles just to dispatch them, right? So in asynchronous multithreading, which is actually really the awesome model that NGINX uses, and the right model essentially, the threads shouldn't block, they just use asynchronous I/O. And after the async I/O has been started, the thread goes back into the thread pool. And thus you need only a few threads, right? 20 or 30, or how many CPU cores do you have? If you have 64, use 64 threads. That's it, right? So a single thread illustrator, very simple, right? Thread doing something, right? Synchronous multithreading, you have all these blocking threads that can potentially block. And asynchronous multithreading, I'm gonna explain this slide now a little bit, right? So these are engine blocks. And they're just sitting on the factory floor waiting essentially for parts, right? So the truck pulls into the loading gate. Finally, we got our pistons, right? And so the worker threads, or let me say workers in this case, they sit around and see the truck pulling in. They unload the pistons, start mounting the pistons on the engines that are ready, right? And then once they mounted the pistons and calibrated them, they can go back to the coffee, right? So essentially, the model here is, if you think of a web server that is hit by a slow attack, right? Thousands of connections that are intentionally slow, right? Or you think of Obamacare or something, right? So this Obamacare web server which had the problems, right? If you remember that. So NGINX handles this with aplomb, right? Because all you need is a little object in memory, which is illustrated here by the engine block, and as long as there's nothing happening, it just sits there, right? And it doesn't consume workers. The workers can do other things where they actually are productive, right? So how does the tokenization microservice now look like, right? What's the architecture? It's actually really simple, right? So you have a JSON parser. We do some cache lookup for config data. So this is just configuration data, how it should be tokenized. It's not the actual tokenization, right? So in case of a cache miss, we do a DB read. We use Postgres. Then afterwards, we use a format preserving encryption, in this case, FF3. This is brand new. It's now NIST certified. So format preserving means, right, that a credit card number, 16 digits, let's say, it stays a 16-digit credit card number. It doesn't have any binary characters in it after tokenization. It doesn't get longer, right? It doesn't have ASCII characters in it, except 0 through 9. That's what format preserving means. And it is beneficial, right? Because you don't have to change your database schema. So anyway, so that's form of preserving encryption. And then JSON output is actually so simple you can do it with sprintf. You don't need really fancy things, you know. So for XML, right, more fancy. Maybe you wanna have libraries for that. But we found JSON output is very simple. For input, you do wanna employ a JSON parser. So let's for 1 minute discuss get versus post, right? So get is intended for short URL encoded requests, and obviously for cacheable responses, which can be arbitrarily long. Post is actually intended, right, for non-cacheable changes to the server state, right? However, we found the get, right, especially get and JSON doesn't really mix very well. For starters, the encoding differs between the essentially binary encoding that post allows you to do and the URL encoding that get requires you to use, right? So you have a few tough choices here. Do you use URL encode only? Well, right? Or do you JSON encode and then URL encode? So in any case, you have to envision a customer maybe copying and pasting these encoded strings on his curl command line, right? CURL to test out your service. And so in the end, we basically, for multiple reasons, we decided to get rid of get and only do post. And there have been other services, I think Dropbox or some other companies that did this very same thing, right? So this is not completely JSON pure, I understand that, right? But we basically use post for everything and never look back, right? Because get seems to be too limited for us. So now I'm actually gonna show you actual source code, so there may be some people who are actually interested in that, and you can start to write your own microservice tomorrow based on this. I'm giving you a recipe here. You start with the NGINX HTTP DAV module, and it's based on put. But put and post are essentially, other than the nomenclature, right, and other than the semantics, are the same, right? So you change the put to post, and you got somebody who's listening on post, right? And then you make this one call. You order NGINX to digest the request body. And what does this mean, right? NGINX is now ordered to digest the request body as it comes in, right? And it can come in very slowly, as you know, maybe during a slow attack, right? So it digests it until you hit the maximum specified length. And we set it to arbitrarily to 1 megabyte, but you can set it shorter or longer, right? And then, you know, once this request body has been consumed by NGINX, once it has been all digested, your handler routine will get called. And now in this handler routine, you put your microservice. And that's it, basically. That's it. I just explained how to write a microservice, okay, for post. For get, it's even more simpler, but as I said, right, get, we didn't really like it, okay? So the more general case is post, okay? So you can have large requests in there, for instance, which you cannot have with get, things like that, right? So now what you do inside, right? You essentially process the request body that NGINX has allocated for you. And now the one caveat, right? The request data itself is a linked list of character arrays. And why is that so, right? Because there are some post methods which are not the counted ones, but kind of they are indeterminate lengths, right? And so NGINX has to cope with that, and hence it does the right thing. It allocates it essentially as a linked list of char arrays or strings, if you want, right? So now you have a problem right there, right? So either you copy all of this data into a large buffer which you allocated, then that's an expensive copy operation. And actually we did this, right? Because the alternative is almost worse, right? you have to now write your own version of JSON parser and strcomp and all kinds of things, nextcar, right? That actually knows, right, about this linked list, that can deal with that, right? So in our case, we just copied it and said, okay, for now this is good enough, right? We basically hit our performance goals. Now I said it, right? So we didn't really bother to do this nitty-gritty work, right, of writing literally, right, your own glibc, right, that string functions, right, that follow a linked list. But if you're a purist, you would want to do this, right? And maybe we'll do it once somebody wants even higher performance. So now, this is now more actual source code. How to walk the post chain, I just explained that it's a chain. So in this case, what I'm illustrating here is this copy method, right? So we copy all these little link buffers into a big buffer, and it's fairly simple code. Right? This is almost too simple for, let's say, an interview or something. So you just find the first buffer pointer, and then while there are still more buffers, you keep on copying them in, right? So the video of this talk will be published by NGINX, so you can just pause the video later and look at this code. It's really simple, right? Essentially, the length is determined by subtracting the post pointer from the last pointer. It's not +1 or anything. It's literally last minus post. That's the length. And here we have a max size. This is just for simplicity, right? In reality, I did this loop twice, right? Once to calculate the correct length, then do the malloc, and then in another loop do the copy, right? So, but this is, in order to fit on one slide, I'm assuming this max size here. It's just a simplification. And so at the bottom, you basically see chain equals chain pointing to next. That means it chains up, it walks to the next contiguous buffer, right? It's a chain of contiguous buffers. And now issuing a response back is even simpler. I said, right, you can use s.f to write a JSON response. It's even simpler. You alloc something with NGINX p-alloc, right? Why? Because NGINX needs to free it eventually. And NGINX needs to free it on its own time when it has completely sent it out of the network, right? So you don't get to deallocate it. So NGINX does. So that's why you cannot use malloc, you use NGINX p-alloc. And you copy your response in there, hello, right? And then furthermore, you allocate this buffer structure, which we just talked about. It's the same buffer structure that we had on input, right? We also use now for output. You PC alloc that. It's called PC alloc for a chain, I think. And then you fill out all these pointers, essentially, this chaining. Now, in this case, we have no chaining because we already know how long our response is. You could use chaining if you want to. Nobody stops you. But typically, you don't need to, right? Because you know how long your response will be, right? And then you do two things. You make two calls. You send the header, right? And you call the call finalize request. And then these allocations that you just made, right? The two allocations which we made, they will automatically be deallocated by NGINX. Now, one thing I didn't show here is you can actually modify the header. You can modify header options. You can, for instance, say application/JSON. But these are really details. They won't impact your testing at all. For a prototype, this is completely good enough. Later, you can refine this by setting custom header options. Now, about what we did, what we did for this project, right? So, what libraries did we use, right? So we used the Jasmine JSON parser written by a Russian guy whose name I don't remember right now. And I discovered it's only a syntax checker, right? It's not a real parser, which means it doesn't really give you the tokens that you need. For instance, it didn't assemble this escape sequence /u or \u and then 4 hex digits, right? So JSON has a way to encode an arbitrary Unicode character, right? And in this case, this parser, the so-called parser, did not actually reassemble that. It just left it as it is. And so I had to modify this a little bit. It's not a perfect thing, but its advantage is really small and simple, right? It doesn't have, you don't need 17 calls to get it to work. You need essentially like 2 calls. And then FF3, right, as I already explained, is a format preserving encryption algorithm approved by NIST since, I think, April or May. And I implemented that as well, but that's not the subject of this talk, right? And then PostgreSQL BDR. This is really an awesome find, right? I just found it by Googling multi-master Postgres. Postgres, unfortunately, in and by itself is only master-slave, right? And then you have a problem, right? You have a problem, what if the master goes down, right? You're down, essentially, right? So I don't know why they even bother, essentially. What is it good for, right? Is the master guaranteed to live forever? Is it some special hardware that doesn't die, right? Right? So anyway, so there's a small company called Second Quadrant in England, and they wrote patches to make PostgreSQL multi-master capable. And that's just awesome, right? You unplug any kind of the nodes, your database stays up, right? Now let's talk real briefly. We have a few minutes left before the questions, before the Q&A. Let's talk briefly about performance here. So first of all, be careful about test clients. I already bashed Java, now I'm gonna bash it some more, right? So Java-based test clients just won't cut it, right, to test this. Because NGINX is so fast. Yes, you're using like the fastest web server on this planet, and you're gonna test it with Java-based test clients, like one of my coworkers. So what you wanna do is use a multi-threaded test tool based on libcurl, right? And we can configure how many threads he launches, and we gave him 3 test machines. Each of them has the dedicated 40 gigabit link, right? Because you don't want the network to be the bottleneck, right? Especially when you give these numbers to marketing. You don't want to give low numbers to marketing, right? So you want to give the good numbers to marketing. You don't want to benchmark on 5-year-old hardware. You want to benchmark on recent hardware, right? It's only fair, right? And this is not even an super expensive hardware. It's, the server runs on a 2-socket Xeon, which has 8 physical cores each, times 2 sockets, times 2 for hyperthreading, so 32. 32 cores when you count the hyperthreading cores as cores. And so yes, 1 million, right, it was achieved. But again, this is operations per second, and it assumes a batch size or a vector size, right? So this is not literally HTTP requests or HTTPS requests per second. So I have to honestly say that, right? And then we implemented another encryption algorithm, which we call random here. And that's a long story. That's basically marketing wanted something else other than FPE, so we gave them something else, and it's faster, right? So this looks like this, right? If you have only a Scala that comes in, you achieve about 60,000 or up to between 60 and 70,000 operations per second. Again, right, this is not the fastest Xeon you can buy, right? The fastest Xeon you can buy costs like $4,000, right? And these are like, whatever, $1,000 CPUs, right? Even with a batch size of 25, so unfortunately these numbers here are very small. So the first one is Scala, right? Batch size 1, essentially. The second is 25. The third is 100. Then 200, 300, 400, 500, 600, and 1,000. So why does it actually go down again? Probably because you're spilling over the hardware caches, right, in your CPU. So you're exceeding the cache size, right? And so the sweet spot, as I said, seems to be about 200. And I'm talking about 16-digit credit card numbers, all of which are wrapped into JSON, right? So you can do some estimate here how long this actually is as a string, right? And, well, we had 1 million per second, but you could scale this now to 48 nodes, and thus, if you want to, you can do 50 million tokenization operations per second, right, in batch. So that means if every infant, child, adult, and old person in the US has just one credit card, you could tokenize all of these 330 million credit cards in 6.5 seconds if you want to. So let's talk about traps and pitfalls real quick. So I think we are fairly well on time, actually. First of all, I already mentioned this, the Jasmine JSON parser is not really a real parser, it's just a syntax checker. And so we needed to put in some modifications, right? Then one crazy little quirk is debug log in NGINX doesn't support %u, right, unsigned. So it kind of does weird things when you use unsigned. So we just use %d with an integer cast. I can live with that, right? Then there's a debug module which you can link into your NGINX build, and we just found it too chatty, right? It logs so many NGINX internals that it's not really useful for debugging your microservice, right? It may be useful for debugging NGINX itself, but not essentially, for the microservice, it does the opposite, right? It kind of, it buries you in output. So I just disabled it and I log at the info level or something, right? And then SA Linux can ruin your day because it assumes NGINX is a web server. And in this case, it's not. You're using it as an application server, right? So, and then here, this one here, what you really want is essentially do asynchronous I/O yourself if you have to do I/O, right, from your microservice. And I mentioned that we do some database operations just for configuration data, and it's just read operations. But I just talked to Igor earlier today, right? And he said NGINX will bring out an application server, right? And then you can do these things nicely. But it's not really planned for official support here to do this, that you can essentially put in your own file handles into the NGINX execution engine. That's not planned to be done. So they don't want to do this, essentially. So they bring out an application server, which is fine, which is probably going to be really awesome. I mean, compared to JBoss or Tomcat, okay? I'm laughing again, right? Okay, right? So furthermore, we found that rate limiting doesn't seem to work in NGINX. So when we enable rate limiting and set it to a very high number of requests, it still limited us to a very low number. And so I implemented my own rate limiting, which worked, right? So I don't know what this is about, but our QA basically said rate limiting doesn't work. I said I use NGINX's rate limiting. He said it doesn't work, so I wrote my own, right? And again, I mentioned this already, the post request comes in as a chain of character arrays, and you can modify now your JSON parser, and then you can modify mem, strcomp, strcompare, and so on, right? The conclusion of this presentation is, okay, let's stop the Java bashing for a moment. If you have millions of lines of code in Java, don't rewrite them all, that's all fine. Just port the speed critical parts to NGINX, where performance counts, right? If it's all like I/O bound anyway, don't port it, right? But if it's CPU bound, like encryption, RAM-based caching, protocol conversion or something. So if you really see the bottleneck somewhere, by all means, port it to NGINX, make a microserver out of it, make microservice and be happy, right? And again, here the take-home message here of this presentation is, right? NGINX is not just a web server for static web pages, but it can be a very fast application server as well. Just write your own microservice, right? All right, and the final page, shameless plug, I would be interested in a job in Europe, right? C, Linux, NGINX, microservice, daemons, crypto, network protocols. And otherwise, questions, please. Yes?
Are you looking for any opportunities in Houston, Texas?
Potentially, email me. I would prefer Europe, however, for personal reasons. Right? My parents are ailing. But Texas is closer to Europe than California. So Yes, right. All right. Any other questions? Any more questions?
How many did you actually, how many encryptions did you actually need per second? Did you need 1 million encryptions?
So that was just for bragging, right? So, I mean, faster is better, right? Actually, but our marketing said this is too fast. How can we monetize this, right? So we cannot sell enough nodes now if one node is already so fast. Honestly, I'm saying this. So can we limit this arbitrarily, right? Can we limit this somehow? And I suggested to him we could charge per like core, like license it per core or something. So if the customer pays for 1 core, he gets only like 1 process, right? So right now, when NGINX starts up, I modified the startup script a little bit. It determines, right, the number of cores this machine has from /prots /CPU info, right? It determines that, and then sets the number of worker processes exactly to this number, right? But you could obviously modify this with some licensing scheme, and we already do crypto, so we could easily do this, right? Have some kind of certificate that entitles the customer to run exactly 4 worker processes instead of 32, right? And so far we haven't done this. So these are just, so yeah, but I literally got the complaint we are too fast, right? Any other questions? Here's one, yeah. We did, and unfortunately, I don't have the scaling numbers here for you, but if you email me, and so my email address is here on the last slide, so you feel free to take a cell phone picture, right, and email me about this specifically, and I can give you these numbers, right? So I literally don't know the answer on the top of my head, or maybe after this session we can look it up on my cell phone in case I have it somewhere. But or email me, right? Any other questions? No, doesn't seem to be. So then, anyway, so have a nice evening in Austin, and thanks for watching this talk. Thanks.